Good afternoon, everyone. Thanks for coming. I'm Lloyd Irland. I'm here to talk to you about climate change, what Maine lakes are telling us. I think this is going to be interesting and would very much welcome comments, suggestions, questions, and challenges when we're done. So I hope we'll have plenty of time for doing that. Let's look at the contents, what we're going to be looking at. First of all, talk about what we are measuring. Second, what are the statistical traits of this data when you arrange it in time series form? We're going to look at some regional examples across the northern US that I think you'll find interesting, and a sample of some of the results that have been achieved so far, some queries and conundrums that I have developed as I wrestle with this data, and then a little comment on what it all means. Photograph here is Pocasset Lake, early stage of ice out in a recent year. Just days ago, this lake was covered about half with shallow pools of water, of meltwater, and we saw snowmobiles screaming across it at top speed, tossing up great wakes of water behind them. Quite a striking sight. Significance? Why do we care about this? Well, ice outs integrate many weather influences and changes in the seasons. There's no one factor that controls ice out date. There are a number of them, and we may not even understand or measure all of them readily. But because they integrate so many factors, I think they are biologically significant. It's noteworthy that other analysts have observed teleconnections with regional weather phenomena, such as the North Atlantic Oscillation, even teleconnections with such things as the El Nino years, and these seem to be able to explain, at least in part, some of the deviations from trend that we observe in the data. The last thing is that these numbers are the only long-term weather measurements we have that go back much further than the 1890s. We have these 4 lakes that go all the way back to 1840, and there's nothing comparable with temperature or any other weather measure. What we're measuring is not always standardized. It's a different rule for every lake. Some lakes are so large and so curious in form that they have to consult several people to decide whether the ice is out. They're clearly not instrumental, but they rely on some rule, such as, well, from this dock, I can see to the other end of the lake with open water, and I'll consider that to be the ice out date. That doesn't mean the ice is all gone. Other lakes have different rules. Most of these observations have been made for business reasons or recreational concerns. None have been made by scientists for scientific analysis, scientific research. But the fact that they were observed for practical reasons may give us a measure of confidence all the same, that they were worthwhile and that people relied on them for some choices they had to make. We are grateful to Glenn Hodgkins of the USGS, the Lake Steward Society, and all the lake groups that have kept these records all these years. Here's a map of where the lakes are. Total of 36 lakes in the sample. And discouragingly, up here in the empty quarter, in the northwest corner of the state, north of Moosehead, we have nothing. It's not that no one's ever there, but they're just not keeping track of this. We'd also light on observations in the whole stretch east of the Penobscot Bay to the St. Croix River along the coast. And even more striking, considering how many people there and how many lakes, York County, we have nothing. Probably someone could find York County observations if they knew who to ask and started digging. I hope someone does. Here's a comparison of, for the whole 36 lake sample, how many lakes actually have observations in any given year. And what you see is up through the 1870s, it wasn't very many. That's why my observations for the longest time series started 1842. The period after 1870 through the late 40s corresponds with a period of much more development of hydropower, much more development of recreation, and much more observation starting to happen. And then we get to a peak between the 70s and the late 90s, and then disappointingly, the number of lakes that are counting observations declines. And this includes some of our oldest lakes that have been copying down the data since the 1890s, they all of a sudden stopped. So our ability to observe this is deteriorating instead of getting better. I have a problem with that, and I hope someone else does too. Here's a display of area of the lakes versus their mean depth to give you an idea of how they array across the size and depth spectrum. And the important thing here is Sebago and Moosehead are the sort of mega outliers, way outside the point cloud that contains most of the lakes. And if you look just at the depth axis, you can see that we have the additional 4 lakes there, in addition to Sebago and Moosehead, that are also beyond the general concentration of the point cloud that is shown here. So this tells you that if you choose a certain number of these lakes for whatever reason and analyze them statistically, the results may apply only to those lakes and not to the others. What you find when you try to do geographic comparisons is that these big lakes frequently fall way off the trend lines that apply to all of the other lakes. Statistical traits. When you array these lake ice updates in time series form, one of the things you see is extremely low signal to noise ratios. The signal is the annual change or the decadal change in the ice update. The noise ratio is the variance of the data from year to year. And we will see this when we look at an example or two. These are volatile, but in most lakes, there are very few real outliers, very few 2 and 3 standard deviation events. The correlations from year to year are very low. And in the short term, though, the trends, the averages may move against trend for some time before they return to trend. And these are called episodes of persistence by the statisticians. Despite these episodes, there's no indication of regular cycles that are about rigid periodicity. And most importantly, for statistical inference, the variances are not homogeneous, but are increasing over time. This is very important for trying to test statistical significance, because the higher the variance gets, the harder it gets to determine whether the signal is nothing but noise. These ice out dates are not synchronous even for adjacent lakes of similar size, and that's kind of interesting. And this points to one of the trade-offs that we make when we're trying to manage long-term trends. We want to use the longest series we can. So I've analyzed 1840 to the present. For geographic comparisons across geographic areas or comparisons with near-term weather, we might want to use a larger sample so we have more degrees of freedom, but we would then have shorter time periods because of what you just saw in the graph before, that most of our lakes don't have long-term time series. For studying the factors influencing the ice update, we're really going to have to use daily and weekly data. And for this, we have far fewer years available. The data are rarely in electronic form that you can actually use, so almost none of us actually do this. We need to cross that Rubicon one of these days. Here's some regional examples that I find interesting and just sort of setting Maine in context. This one is navigation days for lake freighters at Duluth, the western end of Lake Superior. This matters. This counts for business. It means money, and a lot of ships, a lot of infrastructure, a lot of commerce depends upon when ships could come and go on the upper lakes. And these peak out here really for more reasons having to do with the locks and the operational aspects of this than because of the weather. But this is quite a striking change from 200 navigation days to 300 navigation days in just 40 years. Quite a substantial change. Lake Mendota, Wisconsin has been blessed with scientific observers for a very long time, and really has the finest record that looks at both ice out dates and ice in days, so that they can tell you the number of days the lake is closed, the number of days the lake is open. And if you average the first 20 years versus the last 20 years, we have 38 days less of closure on Lake Mendota over this century and two-thirds period. Now, this one is something of an exception to what I just said. This one does have a few fairly extreme outliers, but not many, not enough to invalidate, say, a regression slope, which is what this black line of dots is. Now, here you can see the periodic examples of persistent behavior. Some of them are long, some of them are short. They don't have any regularity to them in cyclical terms. And so you can see a period of time where from the 30s to about almost the 80s, there was really no trend at all, and then it resumed the former trend. There's a famous statistician who once observed that if you torture data long enough, you can make it confess to anything. And this chart gives you an example. It also just tells you that you have to be careful what data period you're examining, and be careful about your kind of statement of conclusions. Here's our closing dates where the ice closed in. This is a very, very long, our very longest one that I know of in the Northeast that is complete so far. Lake Champlain ice closing dates from 1816. And you see a very wide amount of variability here and steady, slow progression. The important thing here is that before 1980, after 1980, it never closed at all for 24 of the years since 1980. And that's a pretty important fact. It just didn't close at all. And you notice that the dates are small numbers. Why is that? Because the lake doesn't freeze until after New Year's Day. Only once did it freeze at that point. Here's a data set, a fine data set of Lake George in New York, an important lake in the eastern Catskills, which has records going back all the way to 1908, and it covers both ice ins and ice outs. And here again, you have this concentration of periods when there was no complete freezing, fairly abundant in these recent years. And what they show you is that if you just look at the years that it did freeze, you have no trend, but this is an extremely important point, and it's hard to know what number to place on that. This does give you a picture. Here's another example. This is Sebago ice outs in 20-year averages to sort of smooth out some of that volatility. And what you see is 16 days of earlier ice outs between 1880 and 99 period and 2000 to 2020. So that's not a small matter. Since the ice in dates at the end of the season often change by a similar amount, it could be that Sebago has gained 25 to 30 days of open water season and correspondingly less of ice out. In the first half of this period, the lake did not freeze 4 times. In the second half, it didn't freeze 8 times. What have been the recent trends? We're very concerned about watching climate change. We're watching it more and more carefully. We're seeing indications in all different directions that it seems to be increasing. It's getting more important. More and more dimensions of climate are showing signs of change. And so what do we see in the lakes in Maine? Well, this is an average for 22 lakes that have the best data for the 30 years 1990 to 2020. And the individual lake SEM slopes, which is a non-parametric test, none of them are significant when you test the individual slopes. When you run this average with a regular regression, the R-squared is so tiny that it's certainly not significant. And you can see the pretty dramatic increase in variance around that regression line in just this 30-year period. And this is not surprising. The climate scientists for all these 30 years, back as long as I can remember, have been telling us that, hey, folks, you're going to see much more variable weather than we have in the past. And this certainly substantiates that. Here's one geographic comparison that I think is quite interesting. This is that if you just get curious and say, gee, I wonder if the distance from the coast has something to do with this. This is a surprise. You have this very tight relationship with an R-squared of 0.8 between the lakes like Sebago that are right close to the coast and then the lakes farther north that are a long ways out. And much of that difference actually appears in the first 140, 150 kilometers, and then the differences sort of tail off, as you would really expect, especially with the presence of weather from the Lake Gulf of St. Lawrence, not that far away from the northernmost lakes at Portage Lake in Aroostook County. So this is a pretty fascinating thing. Clearly, distance itself is not what is at stake here, but distance is kind of a stand-in or a correlate of a suite of meteorological factors that vary across this gradient. Fish and wildlife people in Maine for a number of years have been keeping track of what they call a winter severity index. And the winter severity index is neat because it is available for about 24 different wildlife management districts around the state, so that it's not hard to match up a lake with a wildlife management district, although the match is not always perfect, but it's close enough to be satisfying anyway. And so what you see here is an index that puts together temperatures and crustiness and depth of snow to try to understand how severe the weather is for deer survival and deer population health. And this index, by mobilizing more kinds of data, does give you some pretty neat correlation coefficients, especially for Maranacook and Sebago, where they are quite high compared to any correlations you would get if you just took a relationship with, say, March and April temperatures. Some interesting queries and notes are tossed up by all of this work and by other things I've done and I don't have time to report. One of the question is, are impoundments different? Do impoundments act differently because of the way the water is managed, or do the relationships change between pre-raising of the lake and post-raising of the lake? And more than a few of these lakes have been raised multiple times. What multivariate relationships might work instead of just single relationships between temperature and ice out date? What other variables could be introduced that would improve our understanding of what really is strategic in causing ice out dates to change? What are the size depth patterns with ice out dates? Why are they so weak right now? If we strengthen them with other variables, would they contribute more to our understanding? I don't really know. But if you just look at things that would seem to affect ice out dates in size and depth, you see very weak patterns. A concept that emerged from all of this is to wonder, we seem to be having more winter thaws and winter rain events. And the question, how to measure those and put numbers on them, what are their effects? I wonder if these winter thaws and rain events are a more important dimension of climate than the mere seasonal temperature averages. I think there's a good deal more work to be done to try to understand that better. I have tried to mobilize daily data. It's pretty clear that trying to look at a daily phenomenon with a monthly average is pretty crude way to do it. And yet I haven't been able to get anything out of daily data for the few examples I've had time to discuss. It's very labor intensive, as we mentioned, because we don't get electronic data readily for the daily information. There's a lot to be done there, and I think we could really improve our understanding if we did. A question that comes back to what I mentioned before: have other studies with small numbers of lakes unwittingly introduced bias by the choice of lakes? Have they produced relationships that may not really apply to a wider sample of lakes? We don't really know very well. We'd have to do it over again to see. What does it all mean? Potentially changes in ice-free days on a lot of these lakes by as much as several weeks since the late 19th century. This has got to have consequences for fish habitat, for phenology of the aquatic ecosystem, for migratory waterfowl, for stratification and plankton ecosystems. Now, as a proxy for climate change, with the increased variances that we've experienced, this has weakened the climate signal that's embedded in this data. It's harder to use this as a sense of where the climate is headed, as you've already seen from these pictures. Is this a surprise? Well, maybe it is, but the increased variance is not. It's consistent with what the scientists have been telling us for 30 or 40 years, that climate change is going to be accompanied by more variability. This is just a concrete example. We have seen significant changes in ice-free days or ice-cover days, but accompanying what are really trivial changes in average annual or seasonal temperatures. So the ice regime seems to amplify the effect of very small changes in temperatures. That's kind of an interesting thing to notice. So with that, I'd like to wrap up. Thank you for your time and attention. This is Pocasset Lake again, in a somewhat later stage of opening up, several days before final ice out. And that's myself and grandson Gunnar taking a walk on the ice, as we like to do. So I'd love to have questions and comments. Thank you for your attention.